Hi everyone. In this video, we're going to be talking about continuity of piecewise functions for Math 1451 at Texas Tech University, which is Calculus 1. So this is part 2 of our video series on continuity with piecewise functions, where we've already talked about what continuity is and the types of questions we're going to be asked, and we're just going to dive into these examples about continuity. So in the first example, we're going to be looking at where we're going to state values of x at which a function is continuous. So our question says, determine if the function f of x is continuous. If not, state the values at which the function isn't continuous. So in this piecewise function, remember that a piecewise function is defined differently for different values of x. So for this function, if x is less than or equal to 1, we know that we're looking at the line x plus 1. And if x is greater than 1, we're looking at the parabola x squared minus 1. So part of our first video was talking about how even if we don't know what the graph of these functions look like, we can still figure out their continuity just by using analytical methods. So if you are someone who just really needs the graph to see what's going on, you can do a little sketch of that. Or we can just proceed analytically. So first thing, we know that if a function is continuous, then it has to be defined at those points. So one thing to kind of point out first is that we are looking at x plus 1 and x squared minus 1. And these are both polynomial functions, which are on our list of functions that are always continuous. So for this question, we don't need to be concerned about continuity when we're less than 1 or greater than 1, but just where we transition between these functions, which is at the point x equals 1. So first off, we need to verify that f of 1 is defined. So to do that, we just use the definition of the piecewise function. So when x equals 1, we're specifically in the case of x plus 1. So this is going to be 1 plus 1, which is 2, and that is defined. All good. Okay, so now we need to verify that the limit exists. So because our function is defined differently to the right, meaning bigger than 1, and to the left, meaning less than 1, we're going to take the left-hand limit and the right-hand limit just to make sure that they're the same. So the way that we're going to do this is we're going to take the limit as x goes to 1 from the left. So the way that I remember this is the left is less, so it's that minus sign. So we're going to take whenever x is less than 1 of f of x. So what we can do is we can just rewrite this as the limit as x goes to 1 of x plus 1, which is where how our function is defined to the left of 1. And then we just evaluate the limit like normal. So remember, because polynomials are continuous, to find this limit, we just take the function value at that point, because the function value and the limit are the same. So we get 2. Okay, our left-hand limit is defined. So now we need to take the right-hand limit, where we take 1 from the right side, which is the plus. So again, this is just taking the limit of x squared minus 1, because that's how our function is defined to the right, or at values bigger than 1. So now we just plug in 1. And we are going to get 1 minus 1, which is 0. So this right-hand limit exists. However, these are not the same. So since the right-hand limit and left-hand limit are not the same, the limit does not exist. And the function is not continuous. At x equals 1, because our limit doesn't exist there. So we needed to verify that the function was defined at 1, which it is. We needed to verify that the limit exists, which it's not. But then our step 3 was verifying that those two things were the same. So since the limit as x goes to 1 of f of x does not exist, there's nothing to compare. So we cannot compare the limit value and the function value. Okay, so this is what an example may look like when we're asked to determine if a function is continuous, and if not, state where it's not continuous. So if we are looking at a more simple question, then we're going to have a piecewise where we know that the two functions defining the piecewise functions are continuous. And if that's the case, then we're just going to need to check that point where we transition between functions. However, if we're given something that we know may not be continuous, like a rational function or the trig functions tangent, cotangent, secant, and cosecant, we're going to need to use some other strategies to figure out where that function is continuous. In particular, for rational functions, we know we can't divide by 0. So we are going to need to make sure our denominator is not 0. And for tangent, cotangent, secant, and cosecant, we need to use our knowledge of the unit circle to know where those functions are undefined. So in those cases, checking continuity is going to come down to checking where our functions defining our piecewise are undefined or not. But this is a more simple example, just showing you how to check the right and left-hand limit to make sure the limit exists. So this is going to be it for this video. We hope this helps, and good luck.